Hey, how's it going? I want to start out our first lesson just going over a little bit of math review. Each year, there are several topics in algebra that will come up as we go through pre-calculus where there are some common mistakes that are being made. And so I want to address those. And usually we can refer back to this first lesson here a lot of times throughout the year and being like, remember that first lesson we had with this example and what we said about it. So I wanted to pose a few things to you, see if you remember how to do them. And we're going to start off actually with some true-false questions here. So my first one is, true or false, is x plus y quantity squared the same thing as x squared plus y squared? So pause the video, and I want you to be ready to answer this question, true or false, and not only answer true or false, but to be able to back it up with some good math reasoning. All right, I've taken it that you've given it a chance to pause it and you've answered your question. And let's actually do a little bit of math over here on the left side. Remember that whenever we say something is squared, let's say we have 5 squared, that is the same thing as saying 5 times 5. Or if I have x squared, that's the same thing as saying x times x. So if I have x plus y quantity squared, that's what I've got on the left side here. That's the same thing as x plus y times x plus y. And remember, back in algebra class, a lot of times we refer to this as foiling it. So we'd say first times first, that gives me x squared. First times last, that gives me xy. Inner times inner, xy again, and it's positive here. And then y times y, which is y squared. Combining our like terms here in the middle, that gives us 2xy. And taking the long route here, we see that x plus y squared is the same thing as x squared plus 2xy plus y squared. Now look back up to what we were looking at. We said true or false, is x plus y squared equal to x squared plus y squared? No, it's not. And the difference here is we have an extra 2xy there. Another way we can show this without showing it algebraically is to just actually put some numbers in. So let's choose the numbers 3 and 5. So going back to this right here, if you said this were true, well, let's let x equal 3 and y equal 5 and see if we actually get a true statement. So this would be 3 plus 5 quantity squared. That should equal 3 squared plus 5 squared, right? Well, 3 plus 5 is 8. 3 squared right here is 9. And 5 squared is 25. 8 squared is 64. And 9 plus 25 is 34. These do not equal. So that's just one counterexample to show that x plus y, can't talk today, I got choked on my words, x plus y quantity squared does not equal x squared plus y squared. It's going to happen. All right, I'm going to choke up. It's not so easy talking to the camera like I would be in class. So anyway, that right there is showing that your answer is false. Try out this next one right here. True or false, is the square root of x squared plus y squared equal to x plus y? Pause the video and give that one a try. All right, so I take it that you gave it a reasonable attempt, and maybe you tried algebraically to show true or false, or maybe you tried showing with a counterexample like we did with 3 and 5 that it might be false. I want to solve it first algebraically again. So if we have x squared plus y squared equals x plus y, let's do something like square both sides. So if I square this left side right here, it cancels out that root, and I get just x squared plus y squared. But I can't just square the left side. I also have to square the right side over here as well. So I need to square that whole right side. And when I do that, I get something that looks pretty familiar here. Notice back up on the first problem, what did we say about that statement? We said that that was a false statement. And notice we have the exact same thing over here again, another false statement. So this one is also false. Now, why do I give you both of these? Because they both show up. So a lot of times we will be doing something with 9 plus x squared, and for some reason in the problem we're square rooting it, and students want to incorrectly say that that is 3 plus x, but it's not, okay? So don't fall for that trap there. In fact, it's a good idea to go ahead and remember that when you have a plus b quantity squared, our shortcut for that back in Algebra 1 said that this was equal to the first term squared, the last term squared, and then you take the product of these two in here, which is a times b, and double it. So 2ab. That is what I want you to really know, because that's going to come up all throughout the year. All right. So make sure that you have that memorized. You can also do this with a minus b squared. We call these binomials squared. Square the first term, you get a squared. Square the last term, well, negative b squared is going to be just b squared. Take the product of the two. Now treat this like a negative b. So when you take the product of them, you're going to say negative b times a is negative ab. So negative ab, and then just like we did up here, you need to double it. So you get negative 2ab. And so the only difference between these two when we write them out is that middle term's sign, all right? The one up top is positive, and then the one down below is negative, okay? So having, if you know that, then you won't fall for this trap up here where we want to intuitively say that we can distribute that to, but we really can't, okay? So those are two commonly seen things there that students often will mess up on until after a few quizzes, and then they'll finally get the hang of it. So get ahead of the ball there and go ahead and get that taken care of. Next thing I want you to try here is to do some factoring. So factor, let's do x squared minus 25. In fact, I've already got it written out for you there, don't I? So these are my notes, and then sometimes I accidentally forget to cover parts of them up. If we're factoring x squared minus 25 as the answer over here shows, this is equal to x minus 5 times x plus 5. Why? Well, this is a special case of factoring that we call a difference of squares. So how do we recognize the difference of squares? First, we want two terms or a binomial, 1, 2. Second, they have to be squares, so perfect squares. In this case, we've got x squared, which is a perfect squared, and 25, which is the perfect square of 5 there. And then there has to be a difference, meaning a minus sign in between them. So we could have something like x squared minus 9. That would factor into x minus 3 times x plus 3. We could have x squared minus 100, and that would be x minus 10 and x plus 10 there. The key is you write down the square root of the first term, you write down the square root of the second term, write that down twice, put a minus sign with one, a plus with the other. So if we had 1 minus x squared, it's a binomial. These are both perfect squares, and there is a minus sign in between them. So we have a difference going on here. So I'm going to write down the square root of the first term twice. I'm going to write down the square root of the second term twice. Put a minus with one, a plus with the other, wrap them in parentheses, and that's what this factors out to. And in general, when we have a squared minus b squared, we can say that it's going to be the square root of the first term written down twice, the square root of the second term written down twice, put a minus with one, a plus with the other, wrap those in parentheses. All right, So that's a little bit of factoring there with difference of squares. Let's try out another one here. Try, let's see, y cubed minus 27. So as we look at this, this is not a difference of squares, is it? It is a binomial. There is a difference right here, but these are not perfect squares. But you might notice, hey, they're perfect cubes. So in this case, we can do the difference of cubes formula. So this factors out to y minus 3 times y squared plus 3y plus 9. And so our trick there, if you don't remember that from last year, if you have a difference or a sum of cubes, let's say if it's a cubed plus b cubed, that factors out to a plus b. Notice it's just the cubic root of both of these and the same sign in between. And then we square the cubic root of that first term minus the product of the two cubic roots plus the square of the last term. And so a lot of you might remember that this is the same sign. This is the opposite sign over here. And then this one right here is always positive. So they say same, opposite, always positive. To be honest with you, the difference in sum of cubes do not show up much in pre-calc at least. So you don't really, you can look it up when you need it. It's not going to show up as a surprise quiz or test portion unless I tell you ahead of time, like, hey, we got the difference or sum of cubes. I'll give you some examples. But if you're doing your homework and the problem comes up, just look it up. If you don't remember it then. It just doesn't show up enough to really concern yourself with memorizing it. The difference of squares though, or the square of a binomial, you should know those things. So notice up here, this was a difference of cubes. This one right here is a sum of cubes. The difference of cubes, notice how that's the same sign as right here. This is the opposite as what was previously given. And then this is always positive sign right here. We just took the cubic root of both of these and we said the cubic root of y is y, the cubic root of 27 is 3. Cubic root of, just write it out right here. This is the cubic root y, this is the cubic root 3. And then notice we're gonna square this right here. We're gonna take the product and put it right here. And then we square that last term right there and we get a 9, okay? So that's how we treat that. It just doesn't show up a whole lot for me to spend too much more time on it. One thing I do want to point out though is notice that we did have a formula for difference of squares. And we said that was, write down each square root twice, put a minus with one, a plus with the other. But there is none for the sum of squares. So that, we don't have anything that can factor to. So we're just kind of stuck right there if it stays, if there's a sum between two squares. Difference of squares though, we can factor that out. Difference of cubes, sum of cubes, we do have formulas for those. None for a sum of squares. All right, so keep that in mind as we do some factoring there. Now, let's see, let's do a little bit of practice here. Try factoring a trinomial. So let's do x squared plus 3x minus 10. Pause the video, factor it out, and see what you get. All right, so I'm going to take this. There's a shortcut to factoring these trinomials if the leading coefficient is 1. I'm going to take you through the long route. Now, I know a lot of you had different teachers, and some teachers teach with the Xbox method. Some teachers will teach, they'll say divide and slide. I kind of teach more of a traditional way of doing what I consider to be traditional for factoring trinomials. I really don't care which way you choose. That's always been my policy. If you've got a certain way of doing this math that helps you out, then do it that way. I teach it the way I think is, best for a learner to learn, but maybe you've got a different way to do it. That's fine. The main thing is, are you getting your answers consistently correct? If there's something going on that's making you mess those up, then you need to figure out what it is. If you can't figure out what it is, then find a different way to do it. All right. So that's our key there. We want to be consistently getting those correct as we do them. So let me show you how I do it. I'd say take the coefficient right there, the leading coefficient, the number that's up front, and we're going to multiply it, say 1 times -10 and get -10. And I want to find factors of -10 that add up to +3. So +3 right there. That's going to be 5 and 2, and the 2 is negative. Multiplied, give me -10. Added, give me +3. So I'm going to break up that 3x into these two right here, 5x and -2x. Notice these two add to give me 3x. So I'm not changing the value of this expression. I'm just changing the way it looks. And so this allows me to factor by grouping. And when I factor by grouping, I'm going to pull out an x here because that's what's in common. I get x plus 5. I'm going to pull out a -2 right here. I get x plus 5. And then I'm going to, essentially what I'm doing is I'm factoring out an x plus 5. And I'm left with x minus 2 here. This is my factored form. So there it is, factored. This is where I usually take a moment, though, and I ask my class, I say, what happened to go from here to here? Because almost always somebody says, what happened to that extra x plus 5 there? Like, did it just disappear? And so this is a growing theme I'd like for us to develop in this class, is not to just accept something as fact because I'm the teacher teaching it to you, but to understand how we came up with it or why we came up with it. Now, there are going to be times when I say, you know what, the math is way too complicated to really go through an explanation of why it works or how it works. But when we can, I like to go through and say, this is the reason why. So this was a question I had when I was in high school. I said, what happened to this x plus 5 right here? Because it looks like we're just combining it and making it 1x plus 5. But that's not what's really going on here. Let's, for instance, let's go back to this line right here and write it out again. Okay, now for just a brief moment, to make this a little bit easier to look at in my explanation, let's let the letter u equal x plus 5. Okay, so everywhere in this line where I see an x plus 5, I'm going to put a u in for it. This gives me x times u minus 2 times u. And so now it's a little bit easier to see that what we're dealing with here is a binomial. And so the binomial is x times u minus 2 times u. And if we try to factor that, what do we have in common? Well, we have a u in common. So when we factor out u, we get x minus 2 times u. And remember that u equaled x plus 5. So if I put x plus 5 back in for u now, I get x plus 5 times x minus 2. Oh, that's what we had right here, isn't it? So essentially what this is it's one big binomial. There's only one operator in between those, or a plus or minus in there. And this is one term, this is the other term. And so we're saying, hey, we've got an x plus 5 in common. Let's factor that out. And what's left over is x minus 2. So that's the reason why we show up with just one x plus 5 up here, okay? Let's try another one. This time, oh, by the way, before I move on to the next one, notice the shortcut, if you're wondering what's the shortcut here. Once we had 5 and -2, since the leading coefficient is 1, we can just put that positive 5 right here, same, and the -2 right here, throw the x's with them, make sure you wrap them in parentheses, and we're done, okay? So that's the shortcut, but the key is the leading coefficient has to be 1. You don't have to take the shortcut. You can take the long route each time and split this up, but there are times when the leading coefficient is not 1. Let's try one of those times out. Let's say we had 2x squared plus 7x plus 6. Pause the video, factor that, and see what you get. All right, so Once again, leading coefficient times that last constant there, we get 2 times 6, which is 12, and factors of 12 that add up to 7. It's going to be 3 and 4. Now, here's a case where we can't take the shortcut because the leading coefficient is not 1. So I'm going to break up that middle term into 3x and 4x. And then I'm going to factor by grouping. There's an x in common here. I get 2x plus 3. There's a 2 in common. I get 2x plus 3. A good trick to make sure you're on the right path is that those 2 in the parentheses, they should match up. Because remember, you're going to factor that out. If they don't match up, we probably did something wrong, or you can't factor it using this method. You got to use a quadratic formula or something else. So factoring out the 2x plus 3, we get 2x plus 3 times x plus 2. Always make sure you don't have a difference of squares or nothing else that can be factored out here. There's nothing like that going on, so we say, boom, we're done. Okay. Let's try another example. 3x squared plus x, no, 3x squared plus 10x. Let me rewrite that. 3x squared plus 10x plus 3. Pause the video and give that one a try. Once again, this is a fun one where we can't take the shortcut, so we got to say first times last here I get 9 and factors of 9 that add up to 10. I know 9 times 1 gives me 9 and 9 plus 1 gives me 10. So those are my coefficients for the middle terms here. Factor by grouping. In common here is a 3 and an x. So I'm going to divide each term by 3x. This gives me just x left over. And then divide that by 3x, I get a 3 left over. You always have to factor out something. So in this case, the only thing that's in common between these two terms is 1. So factor out a 1. Factoring out a 1, I get x plus 3. And now we're going to factor out x plus 3. And that leaves me with 3x plus 1. All right, so that's going to give me x plus 3 times 3x plus 1. We're done with that example. All right, so that's, a review on factoring and a couple of those things with binomials being squared and factoring, difference of squares, difference of cubes and sum of cubes. So all those things you're going to see coming up shortly. I want to give you a small review. We're going to do a little bit more review on the next lesson on distance and midpoint. And so we'll go over that as well. And that's also going to cover some Pythagorean theorem. But thank you for watching. Let me know if you have any questions, and I'll give you some additional examples that you can try on your own. Okay? And I'll see you next time.